In this work, we propose a mutual mean teaching framework, which aims at solving the open-set, unsupervised domain adaptation problem in the context of person identification tasks. The task of person identification, or person ID in short, requires to retrieve images of a person of interest across multiple cameras from a gallery of photos. Thanks to the large-scale annotated datasets, deep learning-based methods have achieved significant progress, showing satisfying performance on person ID tasks. However, even trained on such large-scale datasets, evident performance drops have been observed when directly deploying the models to a new scene. That is due to the large domain gaps among different camera systems. Unsupervised domain adaptation, UDA in short, is therefore proposed to adapt the model trained on the labeled source domain to the unlabeled target domain. The present work is based on a clustering-based pipeline, which has been shown to achieve the state-of-the-art performance. Let's quickly review this pipeline. First, it generates pseudo-labels by clustering the person features. Then, the UDA problem can be cast as a fully supervised task with generated labels. The above two steps are alternated until the model converges. Although the model could be roughly adapted to the target domain with such a pipeline, the training of the neural network is still substantially hindered by the inevitable label noise, which is often ignored by existing methods. So how to solve the problem brought by pseudo-label noise? We observed that the model could roughly capture the data distribution. Intuitively, adopting their class predictions as soft labels for training could mitigate the effect of noisy hard labels. But unfortunately, we cannot directly use the network's predictions to train itself, because it will amplify training errors. Therefore, inspired by the widely studied teacher-student models, we propose to train two same networks simultaneously. Each of the networks produces soft labels for supervising the other one in a collaborative manner. To avoid the risk of the networks biasing each other, we further introduce our mutual mean teaching framework. Let's go into more details. In this framework, we feed the same image batch to the coupled networks but with separate data augmentations. Importantly, we construct the mean networks by temporally averaging the network's parameters, and such mean networks are used to generate more robust soft pseudo-labels, which are refined online as the model updates. Specifically, mean network 2 produces soft labels for supervising the training of network 1. And likewise, mean network 1 supervises network 2. Now the question is, how do we optimize the mean networks? Instead of backpropagation, mean networks update their parameters in each iteration according to the moving average formulation. Now you may wonder, why do we need the mean networks for producing soft labels? In conventional peer teaching strategies, the networks are directly trained to approach each other. However, in such a way, the two networks will easily lose their output independence, resulting in error amplification. On the contrary, in our framework, the mean networks provide more complementary predictions, since the model parameters are more decoupled. Now I'm going to briefly walk you through the loss functions. Generalizing classification laws to work with soft pseudo-labels are formulated as a soft cross-entropy loss. To support training with soft labels in the triplet loss, we use the form of Softmax-triplets, where the hard version triplet loss is formulated as a binary cross-entropy loss with a label 1. When dealing with soft labels, it is convenient to replace the hard label 1 to the Softmax-triplets predicted by the mean networks. Here are the results. Compared to the previous methods in unsupervised person ID tasks, our MMT significantly outperforms the state-of-the-art by large margins. We achieved 14.4% improvements in terms of mean average precision on the market-to-Duke adaptation task, and 18.2% on the opposite Duke-to-market adaptation task. MSMT is the most large-scale and challenging public dataset, and we doubled the existing accuracies with our MMT framework. Thank you for your interest in our work. The code is available and you're welcome to send us messages if you have any questions.